Climate change in the Colorado River Basin. An understanding that Earth's climate was undergoing a fundamental change has been part of planetary and atmospheric scientific thinking since the mid-part of the 20th century, when both professional and amateur observers began to track air temperature over time. The connection that linked human activities to that temperature increase came with the work of Dr. Charles Keeling, who was measuring the levels of atmospheric carbon dioxide, CO2, on the Mauna Loa volcano. His graph has become known as the Keeling curve, and that is the graph on the left, and clearly shows a rise in the CO2 concentration. Carbon dioxide is a greenhouse gas, which means that it acts as a barrier against heat that is radiating from the Earth's surface and moving up into the higher levels of the atmosphere. That trapped heat builds up, causing both air and surface, to include ocean temperatures, to rise accordingly. Greenhouse gases, which include methane and water vapor in addition to carbon dioxide, are a necessary component of moderating Earth's climate and keeping the planet warm enough to support life. However, both the scale and speed at which those gases are being pumped into the atmosphere since industrial human activity started in earnest have created an imbalance in the natural carbon cycle. The carbon sinks, those processes and organisms that absorb or remove CO2, can no longer keep up with the sources of released carbon, thus creating a buildup and corresponding heat trap. The chart you see on the right, made with data taken from NASA's Goddard Institute for Space Studies, shows the temperature anomaly, and that is the difference over time of a given average, in degrees Celsius, based on the long-term average between 1951 and 1980. This dramatic increase is occurring on a global scale, and thus presents a challenge for the global community to address together to ensure a sustainable future for all. I decided to look at climate change on a more local scale. The Colorado River Basin connects 7 states in the U.S. and is divided for the purpose of allocating the water resources into the upper and lower basin states. Upper basin states include Colorado, Wyoming, Utah, and New Mexico, with the lower basin states of California, Nevada, and Arizona. According to the Bureau of Reclamation, roughly 40 million people obtain the water they need from this river with its tributaries, much of it being held in reservoirs that spread out along its length. These reservoirs not only store Colorado River water for municipal use, but also provide the means to generate power for major cities in the area and provide water to irrigate millions of acres of valuable cropland. Food, water, and energy are all the result of intensive water management in an otherwise arid region of the country. Water management in the Southwest started in earnest with the settlement of cities around the turn of the 20th century and required the construction of large dams as early as the 1930s. The number of dams in each basin state is shown here, alongside a chart showing the number of counties that support dams, and those are the symbols on the right side. The lower figure, the bar chart, displays the average reservoir capacity for each state in acre-feet. This is a highly managed water resource system, yet it is still very sensitive to changes in 2 major climate variables, namely precipitation and temperature. These charts show the average water content in Lake Mead, which is a reservoir behind Hoover Dam, and Lake Powell behind Glen Canyon Dam, the 2 largest reservoirs along the length of the river, and those that meet the water needs of cities such as Los Angeles, Phoenix, San Diego, and Las Vegas. For both lakes, water levels have fluctuated over time since the respective dams were built. However, it is in recent years that they have been at their lowest capacity. Past changes in the 1960s were due to the building of other dams supporting the system and to water treatment procedures. Recent changes relate to increased demand and reduced supply. The output or discharge of the Colorado River is also changing because of differences in the overall water and temperature cycles. According to White et al., for every degrees in Celsius increase in temperature, the flow of the Colorado has decreased by 9.3%. The outflow from the reservoir, however, has not decreased due to continued water demand, thus creating an imbalance in the volume of water coming in and then leaving the system. This continued deficit will result in water scarcity for the population served if supply continues to diminish, which is a change in climate conditions leading to drought, as demand remains unchanged or increases. According to Lucas and Payton, Earth temperatures have increased in the past several decades, possibly creating the warmest climate the planet has seen in 2,000 years. This increase has created changes in the timing of snowmelt, which affects the entire basin. The headwaters of the Colorado River are in the upper Basin State Mountains, at high elevations where cold temperatures cause the moisture to fall as snow. The layer of snow on the ground serves as insulation that prevents additional snowfall from melting. That water is then still available as runoff to the system instead of being absorbed in the ground or lost to evaporation. The timing of the snowmelt thus plays a critical role in the amount of water that can move from the upper basin to the lower basin states. As previously stated, less water in an already arid region results in water scarcity for millions, especially in drought years. Drought conditions are actively tracked on the NASA GRACE, and GRACE stands for Gravity Recovery and Climate Experiment website. The collected data that measures variations in water stored at all levels above and within the land surface can be used to show multiple water-related indices to include ground and surface water drought. As shown in the figure on the right, which is a heat map, much of the Colorado River Basin has 4% or less wetness, indicating a drought condition. In fact, according to Lucas and Payton, the period since 2000 has been unusually drought-prone for the basin states. Drought is measured by the Palmer Drought Severity Index, the PDSI. The index is based on precipitation and temperature values and provides a number between -10 and +10, with negative numbers scaling to dryness and positive numbers toward wet. The drought severity graph that you see on the left is a chart showing the change in the PDSI since 1895, with data taken from the Environmental Protection Agency website, and it clearly shows a downtrend toward negative values in that same time period, 2000 to present. Those values are close to approaching -4 in the drought condition. As a conclusion, there is no question that the scientific data, the measurements of climate variables such as precipitation and temperature, collected in the past 100 plus years, shows evidence that the planet is warming at an unusually fast rate, one that can be attributed to human activity. The availability of water, a natural resource essential for the survival of all people, is definitely threatened by these changes, as rising temperatures have altered the land's natural hydrological balance and increased the likelihood of drought. This presentation has addressed those concerns, focusing the discussion on a region of the southwest U.S. that is home to millions of people and provides valuable agricultural products to the country. Decreasing water storage levels in reservoirs along the Colorado River Basin should serve as a strong warning that climate change has to be addressed if we are to survive and provide a safe and healthy future with water for those to come.